All right, so this week we're going to focus on vectors. Okay, that'll be the topic for the whole week. I put the section that it is in your book, so if you want to look something up there, it's 8.5. Today will be part 1, part 2 tomorrow, part 3, and then part 4 on Thursday. In the book that we're using, it's section 5.4. Okay, so it's the first section in your packet. All right, start out by just explaining what a vector is. So let's say you had an airplane and you wanted to describe to somebody exactly the way the airplane is moving. There's a couple things you'd have to describe to someone. So like if they were like plotting it on a map, they would know exactly how the plane is moving. What's something you'd have to describe to someone? Yeah? Yes, you have to know the speed it's going. All right, so that's one thing. But if you just said to someone the plane's going 500 miles an hour, it doesn't tell them everything about how it's moving, but it tells them one thing. Yeah?
The altitude.
Okay. Let's see. Yeah, you would, because vectors, if you're thinking 3D, there's a difference between a vector traveling lower and higher. You know, there's a difference. So if you're thinking 3D, altitude would be important. We're going to stick with 2D for now. So you're not going to have to worry really about the height of a vector. But yeah, the direction. Yeah. So a vector is kind of a convenient thing that you can use to represent both of those at the same time. And we've already brought up both examples. Anything that's moving, whether you're throwing an object, a car, an airplane, that's a velocity vector. Velocities have a speed component and a direction component. And force is kind of the same thing. Force has like a component for like, let's say you're pushing on this table. What direction am I pushing or pulling, in which way, and how hard am I pushing or pulling? Robin, do you have a question? All right. Now, when we use vectors to describe quantities that have magnitudes and directions, there's a couple ways we can do it. We can draw the vector out, and I'll show you how we do it. Or we can represent it as just numbers. All right. So if you take a look at this. So this is showing some of the planes that are flying right now. I'm not sure if it's moving. I don't know. Yeah, it is moving. So each one of those planes has a vector. All right. Now it's a 3D vector. So it might look like two planes are very close, but one of them could be like on the ground and one of them could be at 30,000 feet. So you kind of have to take that into account. Like these two planes might be nowhere near each other. Very, very far apart. But if you just think of it two-dimensionally, each plane has a direction it's going and a speed. So if I click on a plane, I can probably see, let's see. So I can see what time it took off. I'm not really interested in that. But there's its speed, okay? 518 miles an hour. That's the speed. It tells me its altitude. And now here's its route that it's flying. Right? Now, all these different things we're seeing here, those are probably when the plane turns. So the plane has lots of directions. Most of the time when we do a vector, it's just going to have one direction. It's not going to keep turning all the time. But they give you the direction as a compass heading, right, from 0 to 360 degrees, where the plane turns, so the latitude, longitude, that's the point where it made the turn to that course, and then how long it flew on that course for. So like it looks like this was one of the longer legs in the journey. It traveled 160, I don't know if that's miles or not, but it's 160 units at the heading of 26 degrees. Okay. So the direction that it's traveling, a little different than the way we do direction. Like usually for us, 0 is to the right, 90 is up, 180 is left, and 270 is down. That's not how a compass works. On a compass, north is 0 and east is 90. So it's a little different. So like this part right here, this direction, 90, is when the plane was traveling east. Right? So direction and speed. Okay. So now it's the job of, if it's coming in for a landing, that there's a tower in Boston or any airport, and they control all the different planes. So computer models basically just look at all the different vectors for each plane, try to keep them certain distances apart for safety. So you can't have two planes like right on top of each other. And everything is controlled, but you could think of it all as vectors. And if you zoom out, you'd see there's like thousands and thousands of planes all going at the same time. So it's kind of important to keep track of all those different vectors. Yeah.
You should zoom out.
Yeah, if you zoom out, what happens is the planes stay the same scale and the states get smaller and smaller. So you can't even see the map at all. So if you zoom out, see the planes stay the same size, but the states get smaller. And as you zoom out, you can definitely see, well, now you can't even really tell, but there's a lot of traffic on the East Coast. Very little traffic, like, you get up into like northern Canada, and you notice it looks like a lot of the paths are curved. Like, this kind of gets off topic a little, but it looks like they're curved. They're not really curved, they're actually straight. It's just because we're looking at the Earth, which is curved, but we're looking at it on a flat board. So, like when you fly to Europe, these planes are pretty much flying in a straight line. It's just you're looking at a curved surface on a flat. It looks like there's probably more planes in Europe. It's just not loading, or maybe it's only U.S. I don't know. Yeah, there's a lot of planes. But again, I bet most of those planes can't even see each other. They're so far apart. I think we tried to figure it out once. Looking at like the density of planes, like if you look at how many planes are in the air at any one time, and then figuring out like the surface area, assuming every plane flies at like 30,000 feet, which isn't really true, but assuming they all fly at 30,000 feet, find the surface area of that zone around the Earth, and take how many planes are in the air on average at a given time, and divide it out and see how many planes there are per square mile at a given time. And it's really not that congested if you think of the entire Earth, but some routes are more heavily traveled than others. Like most planes don't fly up in northern Canada, so you can't really just say that every plane in the world is distributed equally everywhere there's space. Certain areas are more congested than others, so it's kind of hard to say how packed it is. But if you've ever like gone to Boston Harbor and you watch planes, I mean, there's one coming in, at least every 30 seconds into Logan. Maybe not the same runway, but they're coming in from different areas all the time. So, a lot of planes. All right, so the way that you represent a vector if you want to draw it is you use an arrow. Okay? An arrow is something that it's very easy to indicate direction. You just control which way the arrow points. And what about magnitude? Like if you had two planes traveling east and one of them was going 200 miles an hour and one of them was going 400 miles an hour, what do you think the difference between the arrows would be? They'd both be pointing exactly the same way. Yeah?
Move bigger.
Yeah, and it would be longer. So the length of the arrow represents the magnitude. So same idea with force. If you're pushing on something lightly, you'd have a very short arrow pointing in the direction you're pushing. If you're pushing on something very hard, then the direction of that arrow would get longer to indicate more force. Okay, so arrowhead indicates direction, length would indicate magnitude. So there's an example of a vector. Okay, from geometry, you probably called it a ray. And you can use the notation for rays, but we usually don't. I'll show you what we do. Okay, but just like, kind of like a ray, you have an initial point. But the thing is, this arrow doesn't go forever. With a real ray in geometry, it doesn't stop. It just keeps going. Well, if our arrow just went on forever, that would mean like an infinite force or an infinite speed. We don't have that. So it definitely starts somewhere and it stops somewhere. Okay, where it starts, we call that the initial point. Where it stops, that's the terminal point. So this section has a lot of vocabulary in it. magnitude, direction, vector, initial, terminal. So we'll have a lot of terms. But after today, there's not as many. Right. So if this was geometry, you would do something like this. Ray PQ. So that's a notation you see a lot in geometry. What we usually do is represent a vector using a single letter. Now there's a problem with using letters, because what else do we use letters for? Yeah. We use them for variables. Well, a vector isn't a variable. It's a different thing. So if we use a single letter, you have two choices to make it look different than a variable. One thing you can do is just put an arrow over it. Now, when you do something like that, that doesn't indicate direction. That's just an arrow on top of a letter. That means whatever you write below me is a vector. Okay? But you always just have it point to the right. And then you just put a letter in that box. Okay, so that's just a symbol that means vector. Or you can make it a bold letter. If you look at your packet, you'll pretty much see they use the letters U, V, and W a lot on the front page. They do bold letters. Okay. But on page 335, they do talk a little bit about that notation that I just mentioned right here. But most of the time they use bold letters. All right, so a lot of what we're going to do this week is we're going to look at how to combine vectors, whether it be combine them visually by making a drawing, or combine them with doing a calculation numerically. But it's kind of important to understand what happens when you combine two vectors together. So let's think of it in terms of like a force. So let's say there's an object here, and you're pushing on it like that. Okay? If you push on it from the bottom, it's going to move straight up. Now let's say somebody else comes along and starts pushing it at the same time over here. Okay, by the length of the arrow, you're both pushing about equally as hard, because it looks like both arrows are pretty close to the same length. What's going to happen now? So there's a force acting up on that object, and there's a force acting left. It's like two people are pushing at the same time. Chris?
It's going to move diagonally to the left and up.
Right. It's going to move in a new direction, right? And it's also going to move at a new speed, right? If you were pushing at a certain speed and someone else is pushing at a certain speed, well, now it's going to move diagonally at a certain speed, as long as you each keep applying a consistent pressure to what you're pushing on. So the idea is when you add two vectors together, think of it as like two people working together to push on something. You get a new vector. If you were both pushing in the same direction, then what would happen in this case is the direction wouldn't change. But it's almost like the object would move twice as fast, right? If you kept the same amount of pressure the whole time. Right? There'd be twice as much force pushing on the object. Okay, so when you add two vectors together, you get a new vector. So let's look at how you can add V and W graphically. Okay. I think the graphical approach is really, really good when you have a word problem. Okay. If I had to add two vectors graphically, I would prefer just tell me what the vectors are in actual numbers, and I'll just add them that way. Right. But graphically, it's pretty straightforward. Okay. I'm going to show you an example first, and then I'll write out all the steps. So let's say you had a vector that's pointing that way, and a vector that's pointing that way. And you want to combine those together and see what would happen. Well, the way you do it is you position the end of one vector right where the beginning of the next is. So the terminal point, if I make this a different color, so the terminal point of the vector in black lines up exactly with the initial point of the vector in red. Okay. Now, the last step, if you want your answer, would be take what you just drew, look at where you start, follow the arrows till you get to the end. Okay, they should make like a path, and then connect it. That's the answer. All right, so if you want to add two vectors visually, you just stack them together like that, and you just connect where you started to where you stopped. That's the direction. And if you found the length of that green arrow, that would be the magnitude. Okay, so now I'll just write that out. Okay, so you want to add V and W. So you want to position them so that the terminal point of V, which is like the one in black, coincides with the initial point of W, which would be like the one in red. So you line them up like that. And then you draw in that vector in green. That one's going to go from the initial point of V, which is the one in black, to the terminal point of W, which is the one in red. Now, when you write the final answer, it is important that you connect it in that order. From the initial point of V to the terminal point of W. If you do it the wrong way, you would get that. Oops. Are those two vectors off to the side, are they the same?
No.
No. What is the same about them? Something's the same, yeah? The magnitude, yep. So the magnitude of the vectors is the same. You put them on top of each other, they should be exactly the same length, pretty close. But the problem is they point in opposite directions. So it's exactly 180 degrees rotated from where it should be. All right, so the green one is the correct answer. Okay. Any question on that idea? And now you can do this with as many vectors as you have. It doesn't just work for two. So let's say you had one like that, one like that, one like that, and then one like that. And you wanted to know what would be the combined effect if you put all those vectors together. We're going to learn this, but it actually doesn't matter what order you connect them in. Just connect them all. Sometimes it starts to overlap a little bit. That's okay. And look at where you started. Look at where you stopped. And connect where you started to where you stopped. So that is really the effect of combining all those vectors together. Okay. And you can try connecting them in a different order. You'll get exactly the same thing. Right. Just starts to get a little confusing if it overlaps, because then it can be harder to see. But that's not too bad. All right, so let's add these up. Unless you're really doing something precise where you really do want to measure it, in that case you probably want a grid. But if you're just trying to get a general picture, you don't really need a grid. Okay, so we're going to do V plus W. All right, so how am I going to line those up in order to add them visually? Someone just tell me, like, you're going to connect the initial point of this to the terminal point of that. How would I do it? Yeah.
And connect the terminal point of V to the initial point of W.
So terminal point of V is going to line up with the initial point of W. Yep. And I'm going to do it on the grid. Just because if you do use a grid, it does require a little bit of planning. You got to kind of look ahead and say, okay, my vectors are really going down and to the right and to the right. So I better start way to the left so I have enough room. And I might not even have enough room. I think I do. Okay, but sometimes you have to think ahead a little bit.
How do you know which one do you do first? Like which one you position this terminal point? Like Is it just in order of how it's listed?
How it's listed, yep. So V plus W means you're going to take V, just like that, and then put W on the end of it. And this one, it just happens, it does line up pretty nice where it lands at a nice spot. You're not going to have to interpret something like if it's not going to land like halfway through a block or something like that, because that's kind of hard to look at. All right. So it starts here, ends here. And now, what do I do from there to get the final answer? Bob?
Take those 2 points and draw a line. Not a line, but another vector.
A vector, yeah. And from where should I start from?
The initial point of V.
Yes. So I'm going to go just like that. And it's a little hard to see because it's the same color on top of it. But if I go like this, all right, that's a little bit off. About like that. Now, you could probably guess how we would find the length of that. Let me just move this out of the way. If I wanted the length of that vector in red, how do you think I would do it? Yes, yeah.
Distance formula.
Okay, you could use the distance formula because you have I mean, if you had some axes here, you could just put in axes and just say there's one coordinate, there's the other coordinate, use the distance formula. But now the distance formula is really based on what? Okay.
Pythagorean theorem.
Yeah, so all I would do is go like that. And if you really wanted to know the length of that segment in red, just make a triangle out of it and use Pythagorean theorem. All right. We'll get into that more tomorrow when we start finding magnitudes, but it's not very hard to find. Okay, so that's the answer they were looking for. V plus W. And if you wanted, you could give that new vector in red a name. And you could call it vector U or something, but there's no need to. It's a little hard to see, but there is an arrowhead on it. It's just kind of small. Try to make it clear that yours has an arrow. Okay, let's look at this one. Before I add these two up, does anybody have a thought what's going to happen here? Yeah? Going to be a line, like for the final answer?
Yeah.
Okay.
So it's just going to be the same length.
Okay, yeah, they do look like they're the same length.
Because if you're just taking the one of them and just adding it to the initial point, it's just gonna, the W is just gonna go on the beginning of V, and it's just gonna be on top of each other.
Right, they're going to end up being right on top of each other. Now, before I do it, what did we say earlier? When you add two vectors together, you always get what? Yeah? You always get a new vector. Okay, so you have to get a vector. So here's the initial point of V. Oh, actually, let me label it this way. So here's the terminal point of V, which I'm going to line up with the initial point of W. So these 2 points, I'm going to line up. And once I do that, I'm going to connect this spot to that spot. I'm going to connect 1 to 2 after I match the parts that are circled up. Okay, so let's do that. Match them up. And now 1 and 2 are the same point. So I have to draw from where I started to where I stopped, but it's the same point. So there really isn't anything to draw. What happened with these two vectors? You could basically say that they did what to each other? Yeah?
They cancel each other out.
It's like they canceled each other out. When two vectors have exactly the same length and point in exactly opposite directions, they cancel out. Now, what would you put down if this was numbers? If you added two numbers that canceled each other out, what would you write down for an answer? Yeah?
0.
You'd write down 0, the number. Well, this is 0 too, but it's 0, the vector. This is called the 0 vector. So you can write it like that. And think it's less confusing if you just put the arrow over it because it could be hard for me to tell that you made it bold. But the 0 vector, it's kind of a special case. It's kind of weird because it's the only vector that doesn't really have any magnitude and it doesn't have a direction either. So it's a very special case. So is it even really a vector? Because we said vectors have to have magnitude and direction. They call it the 0 vector, but again, it's kind of it's a special case. In your book, talks about that on page 335. Any questions on that one? Okay. So I kind of hinted at this a little bit earlier. I'm going to show you visually how this works. This part's kind of hard to do in your notebook because I'm going to be dragging things around a little bit. So it might just be something you want to watch as far as why this works. So remember, commutative means you can change the order you add two things in, and you get the same answer. Now, you might be saying, well, yeah, you can always change the order you add two things in, like 2 plus 5, 5 plus 2, same thing. You can't assume that anything that you know about numbers works with vectors. Some things do, a lot of things do, but not everything. Like, there's a type of multiplication we're going to learn later in the week. We've always learned that multiplication with numbers is commutative. 6 times 8, 8 times 6. Same thing. Well, there's a type of multiplication with vectors that is not commutative, meaning if you change the order, you get a different answer. Right? So you can't assume that what you already know about numbers works. Let's look at how this works. So visually, I'm going to show you what happens if we do it in the order on the left and then on the right. So here's V, and on the end I'm going to add W, and I'm drawing everything by hand, so it might not come out exact, but I'll try. Okay, so there's V plus W. Now I'm going to do it the other way, W plus V. So take W and put V on the end and connect it. And let's compare that to what we had before. Again, I drew it by hand, so it's not perfect, but it's pretty close. So I'm just showing you that W plus V and V plus W comes out the same. Right. Now, how about associative? Associative doesn't have to do with the order. That's commutative. Does anyone remember what associative has to deal with? Yeah?
A certain thing equals another certain thing. There's that.
It's going to be some stuff on the left equals some stuff on the right. So there's going to be an equal sign in here. But does anyone remember like what that has to do with associative? Well, if you think about associate, right? If you talk about who you associate with, what does that mean? Like when you associate, how do you do that? Like, do you do it alone? Like, what does that mean? Yeah?
Is it how the numbers are grouped?
Grouped, right? How things are grouped together. What things are grouped together with what things. So when we want to group things together in math, what symbol do we use? Yeah.
Parentheses.
Parentheses. So notice the order is exactly the same on each side. ABC, ABC. Okay, but on the left, A and B are best buds, right? They're in parentheses. On the right, B and C are associating. They're together. Right? So just think of it as like associative is who you associate with. The friends are inside parentheses. So it's just changing who's with who. So let's try it the way on the left. I'll add A and B first, get the answer, and then add C on the end of it. So here's A and B. Add those together, I get that. I'm just going to put this back where it was. So that's A plus B. And now put C on the end of it. Okay, so that one looks kind of like that. And we don't need that. Okay. So that was the way we did it on the left. Now let's do it on the right. So B and C, add those first. Here's B. Here's C. And And there's b plus c. Now take a and then add b plus c on the end of it. So here's a. And then put b plus c on the end. Connect it. And let's see how close it came out. It's pretty good for just doing it by hand. So associative property, you can change the order you add things in. Sometimes I change the order and group things together that look easier to add first. Just depends on the problem. So questions on those two properties? All right. What would be the difference between those two vectors? So you have vector v, and then a negative in front of vector v. What do you think the difference would be? Yeah? They would point in opposite directions, but what would be the same? Yeah? Yeah, the length of them. So the difference between these vectors is the direction they point. Specifically, they point exactly in the opposite direction. One's rotated 180 degrees. But they have the same magnitude. We saw this earlier in an example where we got the zero vector. And here's the same thing written out. Slightly incorrect, actually, so we need to fix that. But we had this idea where we had a vector, we had its opposite. Now, why did I say this is incorrect? What's wrong there? Yeah?
It doesn't say that 0 is a vector.
Right, that's impossible. You can't add a vector to a vector and get a number. That's what that's saying. That doesn't even make sense. So, it's a small thing, but it is kind of important. So if you add a vector to its opposite, we get the zero vector. Now, knowing that putting a negative in front of a vector, all it does is flip the vector around, that's going to help us to subtract two vectors. Okay, we've added two vectors visually, now we're going to subtract. Well, what if you wanted to subtract 3 minus 2, but you didn't quite understand subtraction? All you understood was addition. What calculation could you do with addition that would give you the same answer as 3 minus 2? Yeah? Yeah?
3 plus negative 2.
3 plus negative 2. So anytime we want to do a subtraction problem, we can treat it just like an addition problem. Just take the number that was first, that just stays the same, but take the opposite of the second thing and add it. If you add the opposite, that's really subtracting. And with vector, what does opposite mean? Points the other way. So now we should be able to subtract two vectors. Take the second vector, flip it around 180 degrees, find its opposite, and then add it. And that's how you do subtraction. Okay, so next we'll try an example with subtraction. All right, so we have V and we have W, and they want us to subtract them. Okay, before I'm ready to subtract, I need to find something first. What other vector should I get first here? Yeah.
The opposite of W.
I should get the opposite of W. So if you're using computer or even by hand, it's not really that hard to find the opposite, but I can find the exact opposite just by taking this and flipping it twice. If you do a horizontal reflection and then a vertical reflection, that's exactly the same as rotating something 180 degrees. It's from geometry. Okay, so now I have negative W. So, Tori, how am I going to think of this problem? Instead of V minus W, how am I going to think of it as addition?
V plus negative 2.
v plus negative w. And that's it. So take v, add negative w right on the end of it, and then connect where you started to where you stopped. And that's your answer. Okay, and that's how you subtract two vectors. Any questions on that? Okay. All right, so scalar multiplication. So I told you that there's a type of multiplication you can do with vectors where you change the order and it doesn't make a difference. Or, well, it does make a difference. This is not that. We're not going to be multiplying vectors times vectors until Wednesday and Thursday. This is a type of multiplication, but it's not between a vector and a vector. It's between a number and a vector. And if you look at the first word, it kind of tells you what's going to happen here. Scalar. Think of the word scale. What does that mean if you scale something? Yeah?
Can get bigger or smaller diagonal.
Yeah, it makes something usually bigger or smaller. Maybe you make a large scale diagram, like if you were modeling like a cell or something in biology. Maybe you want to see it larger, so you make a large scale model of a cell. Or maybe if you have a house and you want a model of it, usually that would mean you make a small scale version of it. So this is when you multiply a vector by a number. So it would look something like this. 3v. That's not a vector times a vector. That's a totally different thing. That's a number times a vector. And that's called, the number in front is called your scalar. So the result is a new vector. Now Allison said two things that could happen. It could get longer. It could get shorter. But there's actually a third thing that could happen. And we don't scale by the number 0, because that would just wipe your vector out. But what, does anyone know the third thing that could happen? Besides the vector getting longer or shorter?
Could it change directions if you multiply it by a negative number? Yes.
It can change direction in a very specific way. It can't just arbitrarily change to any direction, but it can point exactly in the reverse direction if you multiply by a negative. So that's the three things you can do with scalar multiplication. Make a vector shorter, make it longer, or flip it around 180 degrees. And again, that number in front, it's like a scale factor. We call it a scalar. Okay, so eventually we'll be scaling vectors and just kind of combining the results numerically. I'm going to show you how to do it visually to start with. Okay, so they gave us the vector v, and they want us to find two things, 2v and a half v. So Gabe, if I wanted to find 2v, and I wanted to do it pretty precisely, I don't have a ruler I can use, but I don't really need one. What could I do with this to find 2v?
Just copy it.
Yeah, just make a copy of it. And then what?
Just attach one terminal to the other initial.
Yeah. There you go. There's 2v. Just draw in your answer. So that's 2v. Now to do a half v, I don't really have a way that I can scale something by 50% in this program. So I just kind of have to estimate, halfway looks like it's about maybe right there. So just draw in an arrow. And that would be about 1/2 v. So neither one of those scalar products changed the direction because there wasn't a negative. Let's look at this one. So they gave us v, and they want me to find negative v and negative 1/3 v. So Emily, when I find negative v, what's going to happen there?
It's gonna rotate 100.
And what about the length compared to v?
It'll stay the same.
It's going to stay exactly the same. Right, so we make a copy. And it's not that hard really if you want to sketch it by hand, but it's also not that hard for me to just go like that. So that's exactly negative v. Now that I have that, I can use it to get negative 1/3 v. Negative 1/3 v. Well, Madison, how's negative 1/3 v going to compare to negative v? What's going to happen?
It's gonna be a third of it.
A third of the length. So I'll just try to estimate where you think a third would be. Maybe about like that. And there's negative 1/3 v. Any questions on that one? So again, scalar products. All right. So now let's do. No, let's just do the second one. We'll just do 2v minus w plus u. Now, before I do this, I kind of like to have all the different pieces that I'm going to have to put together already done. Okay. So what am I missing that I'm going to need here? Yeah. I need negative w. So why don't we create that. Again, whether you use the arrow or the bold letter, I'm just kind of using both interchangeably. All right. And for this one, I'm just going to kind of do it by hand. All right. So there's negative w. Now, if you want to have a location, like on the grid, you kind of need to plan out ahead of time what's going to happen. So v is going to bring us up and to the right, w up and to the left, and u is up and to the right. So we're going to be moving up a lot. So I would start down pretty low, and I would also start more maybe in the, I would probably start like right around here. It's probably a good spot. All right, so let's start with 2 v's. So take 2 of those and put them together. So we got 1, 2, pretty close. All right, so we got 2v. Now we're going to add the minus w, which is going to bring me back to right there, and plus u. So just take that, put that right there. So again, we landed at a nice coordinate, which again, most of the time that'll happen. So we start here, we finish there. Now, to get my final answer, what's my last Chris?
Connect the two.
Yep, and which one should I start at?
The initial of the V and
Yep.
end at the terminal of the U.
So about like that. Okay, so again, the answer is a new vector, and it points in a new direction, combining all those together. Okay, any questions on that? All right, so different symbols we're going to see. This is one of them. When you put double bars around a vector, that symbol means magnitude. It's kind of like absolute value, but they use double bars for vectors. And all that symbol means is basically they're looking for the length of the vector. Now, I didn't really go through an example of how to find it yet. I mentioned you could just use Pythagorean theorem, but we'll do that more tomorrow. Now remember, since it's a magnitude, magnitude means the length of the arrow. Lengths can never be negative. Doesn't matter if the vector points down. It still has a positive number when you measure how long it is. Okay, so what I have there is it says the magnitude of v compared to the magnitude of negative v. What would be the difference between those two things? Magnitude of v and the magnitude of negative v. Nothing. There is no difference. Those two magnitudes would be exactly the same. What is different about them is the direction they point. But magnitude doesn't really take into account direction. It just takes into account how long something is, not which way it points. So something special that can happen, and we've talked about this word before when we did unit circle trig, is the idea of unit meaning 1. Unit means the number 1. So if you get a vector that it comes out to exactly 1 unit long, that is called a unit vector. Now, we're going to talk more tomorrow about, well, what happens if you get a vector, it doesn't come out to a length of 1, and you want to make it a length of 1. Well, you can do that. You can scale it. If it's too long, you can make it shorter. If it's too short, you can make it longer. So you can always make a vector 1 unit long if you have to by scaling. You just have to figure out what to scale it by, which means you've got to figure out, okay, how long is the vector I have? All right, it's 12. All right, well, I'll scale it by 1/12. That'll make it 1 unit long. Okay. Or maybe I find the length of a vector and it comes out to 0.5. All right, we'll double it. Double the length, and it would make it a unit vector. Usually when we make something a unit vector, we don't want to change its direction. We're just forcing the vector to be 1 unit long for whatever reason. Okay, but that's what unit vector means. All right, so if we really want to start to do some things with vectors, and it's not going to take forever, we got to kind of get away from drawing. Okay? I still think drawing is good for a word problem, not really if you just have to do something basic. Right? Like if I had to add 2 vectors together, I'd rather you just give me a numerical representation of the vector than an image. Because then I need graph paper, I need a ruler, it takes a while. So there's 2 ways we're going to talk about how to represent vectors that are not graphic. In the first notation, your book calls an algebraic vector. I'm not sure that notation is universal. Like I haven't really seen that notation a lot, but that's the term your book calls it. The next notation we're going to learn, that name I have seen everywhere. It's a very, very common name. I just haven't seen this name as much. So when you write something as an algebraic vector, that's how it looks. It almost looks like a coordinate, but instead of parentheses, you use angled brackets. Kind of like a less than and a greater than. And what the A and the B tell you are basically components of the vector. It tells you from a starting point, how far do you move horizontally? And how far do you move vertically to get to the end point or the terminal point? So think of A and B as directions, right? Telling you how to get from somewhere to somewhere else. And I write that down right here. So from an initial point, A tells you how far left and right to go. And then from an initial point, B would tell you how far up or down. So A and B are directions from the initial point to the terminal point. Okay, and if you really want to spell it out, I mean, I said A is left and right, but A, that's your horizontal. B is up and down. Up and down is your vertical. Now, if we were doing this in 3D, you would need a third component. Because A is like your x-axis, B would be your y-axis movement, and then C would be your z-axis movement when we get to 3D. Okay, so next thing I'm going to show you, I'm just going to give you an example of a vector that's in what your book calls algebraic form. An algebraic vector. Let's go like this. Okay, so there's an algebraic vector. 2, 3. So the 2 is the horizontal component, the 3 is the vertical component. What doesn't it tell me though? There's something that notation doesn't really make clear. Because I want to get ready to draw that. Yeah? Starting point. It doesn't really tell me where to put it. Where do you put it? Doesn't matter where you put it. Put it anywhere you want. So, start here. And is everyone good on the left so I can make the right bigger? Okay. So the vector is 2, 3. Right 2, up 3. That's a perfectly valid picture of the vector 2, 3. I could go here. Start here, 2, 3. There's another picture of the vector 2, 3. 2, 3. I can put it a bunch of different places. But there is a common place that we usually start from, which I haven't done. But where do you think we normally would start from? Yeah, we normally start from the origin. So if you draw a vector and it starts at the origin, that is called a position vector. Okay, so a position vector, just a vector with its initial point at the origin. Okay, so the next thing I'm going to do is I'm going to take one of those vectors I just drew. Maybe I'll draw one more. We're going to take one of them and we're going to convert it into a position vector. Okay. Now we already know what the answer is. We already know it's the vector 2, 3. But say you had this picture, 2, 3. And they gave you that picture and they said, write an algebraic vector for that. Right? So they wouldn't tell you it's 2, 3. You'd have to figure that out. All they might give you is the coordinates. Right? And they might not even give you a picture. They don't have to. They would say, okay, the vector starts at 3, 4. That's the initial point. And it ends at 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. And using the initial and terminal point, it would be your job to somehow figure that out. Does anybody see what you could do with the coordinates to get the vector 2, 3 out of all that stuff? Yeah?
Subtract the terminal coordinates or the initial from the terminal.
Yeah. Take your initial and subtract them from the terminal. 5 minus 3 gives you 2. 7 minus 4 gives you 3. And it is important you do them in that order. If you switch the order, you would get -2, -3, which would be pointing the wrong way. You'd have a negative horizontal component and a negative vertical component, and you want them both positive. All right, so that's important. All right, so to find a position vector, you'll be given an initial point and a terminal point. If they don't specify which one is which, and they just give you labels, always assume like P1 is initial, and the one that comes after it, P2, is terminal. So that's the order they'll always give it to you in. Initial, then terminal. Okay, and as Natalie said, that's exactly what you do. You just subtract them. Terminal x value for this x2 minus x1. So it's your terminal x value minus your initial x value. Your terminal y value minus your initial y value. Always terminal minus initial. And when we have to extend that to 3D, very, very easy. All we're going to do is put comma z2 minus c1. That's pretty much all we have to do to take every formula we're going to learn all week and extend it to 3D, is just look at the pattern and do the pattern one more time for the z's. So we'll look at 3D more on Thursday. Okay. Any questions on that formula before we finish up with an example of that? So they're not really specifying which one is initial and terminal, so always just go by the convention. First point is initial, second point, terminal. Okay, so find the position vector. To find both components, the horizontal and the vertical, what math operation do we use? Yeah, subtraction. So we can set that up right now. There's your subtraction. And let's start with the horizontal. What's going to be my calculation to get the horizontal component of this vector? What minus what? Yep, we're going to have 4 minus -1. And Emily, how about to find the vertical component?
6 minus 2.
6 minus 2. Okay. So Kathleen, when I do that out, what do I get for a vector?
5, 4.
You get 5, 4. So that means this vector starts, if you started at the origin, it would end at the coordinate 5, 4. 5 right, 4 up from wherever you start. Okay. Any questions on that? Okay. So the thing that gets a little tricky sometimes with vectors is word problems. Tomorrow we're going to look at a word problem. And one thing you have to kind of remember is how to solve something like this. That's going to come up at some point. So remember, you can use substitution. That's probably the easiest way to solve. Okay, I'm not actually going to solve this one, but substitution is going to come up. And the other thing that's going to come up is right triangle trig. So just remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's just your SOHCAHTOA. Okay. That comes up in the problem. And I think that's it. So those are the two things that come up in the word problem that you need to know, right? Triangle trig and solving a system with substitution. The rest of it I'll show you tomorrow. Okay, so remember, homework, when it says 344, that's not in your book, that's in your packet. So it's 1 through 10 all, 14 to 22 even, and 26 to 32 even. Now, the directions on 26 to 32 ask you to do something we haven't done yet. We're going to do that part tomorrow. So for 26 to 32, all you have to do is find the position vector. Okay, that's it. Also, just a reminder, a lot of people were pretty good last week about coming to make up that test. If you made it up, I graded it, it's online. If you haven't, remember you have until Friday to come get that information. Actually, really Thursday, because we don't have class on Friday.